Well, the next type of problem is one I would call a stability problem. We solve some of these in 2 dimensions in a somewhat similar way, but if an object is about to tip over, then we would call it a stability problem. We may find out what force it takes to tip something over. So what have we got here? I've got this cart. It says that it's weightless, in other words, has no weight. It's got 3 wheels, and it has a couple of applied forces. And what our problem is if I apply an unknown force right there, how much force does it take to tip over the cart? The force P to tip it over. Now, a couple things to recognize. Remember when we did this in 2 dimensions, we said, what happens when it tips? Well, in this case, instead of rotating about a point, it's going to rotate about an axis. So here is our point A. It's kind of, the view is underneath the cart, so you can't really see it directly, but you can see the little shadowy figure there. But it would rotate about AC axis. It would rotate in this direction, about that axis, if I were to push too hard on that. So in other words, at tip, rotates about AC, and what happens over here? B goes to 0. So that's the same kind of thing that we did before, and that's what we do in 3D. Alright, so I don't see any axes identified here on the picture, so I'm going to define some axes, and I'm going to call this my x-axis. This will be the y-axis, and then the z-axis kind of comes from that point right up there. Now with that, I can do same kind of technique. I can sum the moments about the x-axis. Here I have all the dimensions noted, but I do have this unknown force. So I'm going to say P times that 8 inches going in that direction, minus the 380 times this distance, also going in that direction, minus the 800 times this distance going in that direction. All of those are going in that direction. What goes in the other direction is the reaction here at C, and it's going to go this way. So I'll say C, and the lever arm here is this full 35 inches over here. I can also put the B in here, but however we have identified that B is equal to 0, and so now I have an equation here of P and C, which are both unknowns. Let's look at it through the y-axis. I got 800. Well, actually P goes through that axis, so there's a 0 lever arm there. If I have this going, the P going in this direction times that, then I'll have the 380, I beg your pardon, the 800 times the 12 inches, then I got 380 times the full 24 inches. Those are both going in that direction. Going up, I've got B, except B is equal to 0, and up there I'll have A going in this direction, and it'll have a lever arm of 12. So here's my equation. Some of the moments about the Y, 380, 800, then I got A, and again B is equal to 0. So I'm setting this up here where I've got quite a few unknowns. Have I been able to solve for anything? I still have P as an unknown, C as an unknown, and now I have introduced yet another unknown. So let's sum the forces in the Z. I've got 380, 800, and P, which is my unknown. A and C are also there. So if I sum the forces in the Z, I got P, A, again B goes to 0, and C, and then I have this. I got 3 equations, 3 unknowns. We have a good way of solving that using RREF, and so I'm just going to zoom in just a little bit so you can see how I set this up using my calculator, where I will say sum of the forces in the x direction is my first equation, looking at P, and then my 3 unknowns, P, A, and C, have to be equal to a constant. If I look at P, I have a minus 8 as my coefficient. There is no A, so that's equal to 0. And C over here has a positive 35 as the coefficient. If I add these two together, I would get 31,600, negative 31,600 on this side of the equation. However, the way we have to set this up with RREF is it goes on to the other side of the equation, becomes a constant, and when you do that, you change the sign and you set up the first equation. Similarly, you do the other 2 equations and then you hit RREF and you can solve. So anyway, that's a great way of doing that. If you want to do that on your homework and exams, I certainly don't mind you using your calculator using RREF. Well, the next type of problem here is another three-dimensional problem that I call this a table that tips over. Obviously, it is a table that's tipping over. It's got four legs in a cross pattern here, which is very typical if you look at your office tables or table at home. And if you push too hard on the table like this, it will fall over. And what this little problem is all about is that I have a force that's going to be applied to the corner, and I'm going to apply the same magnitude of force on this corner, pushing in this direction. I can either pull it from that corner or push it on that corner. It doesn't really matter. Both of these added together, or when we add them, or when we consider them together, will cause the table to tip if we push too hard. So here again, our question is, what happens? So you can see that at tip, it's going to rotate about this axis and tip over in this direction. So I don't see any letters on this picture, so let's define some letters. So I'm going to call this point up here A, and this one B, C, and D. I've got a point O defined there, but I didn't use that. I don't have any axes either defined, so I'm just going to invent some axes. I'm going to call this axis X, this axis Y, and then Z is coming right up through the center of the table, going up like that. Alright, how can we resolve this? It's easiest to use moments about the axes, so let me just show you what we've got. About this axis. Okay, first of all, let's go back to what happens. At tip, it's going to rotate about this axis, and now that's going to be the AB axis. When that happens, the forces over here go to zero. In other words, as it rotates about this axis, it goes this way, the forces here equal to zero, the reactions equal to zero. So that's just kind of the important understanding about how it works. Now if we sum the moments about that axis, we can try to figure out something. Alright, so I have a force pushing down here. Does that have any tendency to rotate about this axis? And indeed it does. It has this lever arm, which is half of 5.5. So I'm going to say that that is minus P times 2.75 for that. How about this force? Does that have any moment about the x-axis? And it does not, because it is parallel to the x-axis. What other forces do I have about the x-axis? Well, these are both zero. A is on the x-axis, so the only other force I've got is B, and that's going to be pushing up. It wasn't a very straight line. It's going to be pushing up with this lever arm. So here I've got an equation, some of the moments about the x-axis. I can't solve for either of those, but I can find out that B has some relationship to P. How about let's sum the moments in the y-axis? Alright, in this case, the P does try to rotate about the y-axis. It's trying to rotate it in this direction. And the lever arm is going to be this half of 3. And so that's going to be in the negative. It's trying to go in the negative axis like that, trying to go that way. And so I'm going to say that P tries to go that way times 1.5. That's what this one is. How about this P? Does this have a tendency to rotate about the y-axis? And it does. And it acts through this lever arm. In other words, this lever arm is right there. So I have P times 3. Now what is resisting anything? Let's say about the y-axis. We know that D is equal to 0 when B goes through the y-axis. And C is going to 0 at the end of the day. So A is pushing up like this, and it has this lever arm of 1.25. And so that's what that's all about. Again, I can't solve for anything yet, but I have A as a function of P as well. Now let's just sum the forces in the Z direction. I didn't draw the weight on here yet, but the weight is considered to be uniform, and is going straight down through the middle of the axis, and I said that it equal to 100 pounds. So if I sum the forces in the z-axis, I have this equation: minus P minus the weight plus A plus B is equal to 0. And then using these pieces in here, I can solve for P is equal to 20.8 pounds in order to tip it over. So again, it's a pretty powerful concept. This is something I want you to understand here for three-dimensional equilibrium.